Hello, everyone. Welcome. I'm going to be talking about chemical history here and some of the implications for teaching and learning. I have been reading about chemical history for the past couple of years and want to go through some of the things that I've learned, but also some of the connections I've made in my own classroom. If I start by introducing myself, my name is Scott Milam. I teach at Plymouth High School. I'm in my 16th year of teaching there. I'm sorry, 16th year of teaching overall, 12th year there. And I currently teach IB Chemistry HL and Honors Chemistry. You can follow me on Twitter. I run a YouTube channel. I've written a fiction book, and I also work for Pivot Interactives and the American Modeling Teachers Association. And what I want to start by talking about is that as you go through teaching, there are ways to improve, even when you kind of start to get things under control. So in year 14, I had just added in modeling instruction as well as cognitive science practices, and you can see that there was an impact, sizable impact on my IB scores. And so this last couple of years, I've been working on how do I hone the history of chemistry in a way that's productive towards teaching. So I also want to start by saying that I have no official expertise in this. This is all from me reading lots and lots of books and using this within my classroom, but I have not done any official training on chemical history. I would also add that knowing chemistry and the current models that we use can be sometimes counterintuitive towards deconstructing chemical history. And so having knowledge of chemistry can often make it challenging to go back and view things through a lens of the 1800s. I would add, of course, that this talk tonight is going to be focused on Eurocentric chemical history in the 1800s. And so prior to Boyle, Van Helmont, the empiricism group, I don't know very much. And there's a lot of history there in terms of Arabic chemical history and Chinese chemical history. And I'm not familiar with it as much, but know that that's just omitted here. And lastly, everything that I know tonight, I've mostly learned from reading, and so pronunciations might be a little bit of a mess as we go through. And let's kick things off with a couple things. So the first thing I want you to do is I want you to pause the video for a second. I want you to go through this list, and I want you to identify how many of these have you heard of, how many of them have you not heard of, and for the ones that you have heard of, do you know what they did? So go ahead and pause for a second and just kind of go through and do a quick analysis of that. And I'm not going to wait for you, I'm going to go right on, but I want you to spend a second doing that. The second thing I want you to do is I want you to pause this video again, and I want you to look at these 8 major historical milestones in chemical history. We call this A, B, C, D, E, F, G, H, where A is the Van Helmont, Robert Boyle, E is the Irving Langmuir, and Gilbert Lewis. If you go through those, what would you put as being the first historical event in that group? And if you want, you could also go with what do you think was the most recent thing to happen. But in particular, I want you to look at, do you know of those which came first? And so the reason why I do that is because when we teach, we tend to teach things in orders that don't align with what happened in terms of historical chemistry. The first thing that occurred on there was Boyle and Van Helmont going through empiricism, or replacing the 4-element theory. But one of the last things to happen on there was chemical bonding. And so I want to start actually skipping ahead to later in history for a moment to point out that our first functional models of bonding were not until we were starting to progress into organic chemistry. And in addition to that, the models that we use now, valence bond theory, didn't come about until the early 1900s. And really, the idea of a covalent bond in particular didn't come out until 1916 with Gilbert Lewis, and that was then popularized 3 years later by Irving Langmuir. So when we teach bonding early in chemistry, we're providing students with an out in a way that we didn't have in terms of chemical history. So when we went to explain things in chemical history, we wouldn't use bonding to be able to kind of conjure that up. There wouldn't be a knowledge of electrons or a plum pudding model until much later. And so when we do this, when we go through stuff tonight, I want you to think about the fact that if you could not use that to explain things, how much more difficult would that make it? Because with that, it becomes very impressive. So our big shift into electrons incorporated a little bit is when we started to work with charge. And that started primarily around the actual 1800, not the 1800s, but Alessandro Volta constructs the voltaic pile. Berzelius and Davy, of course, both use the voltaic pile to analyze chemicals. So Davy isolates, I think, 9 elements, including sodium, potassium, a bunch of the alkaline earth metals, and a few others. And basically, they had these alternating disks of 2 different metals with a brine-soaked solution in between that allowed them to construct a current and a voltage. And they would apply that to different chemicals to be able to do different things. Now, Berzelius constructed a rough model of bonding from that called dualism. And dualism functions very well for us today in terms of ionic bonding. It says that some elements are positively charged, other elements are negatively charged. And so before we get to that, let's come back now and go back to the beginning. So outlining the beginning of chemistry is always a little bit challenging because do you count alchemy? Do you count things of which we don't have very much written record? That's always a little dicey. And so for a lot of people, there's different levels. I'm going to start and kind of assign Robert Boyle to be a big shift in milestones that is a reasonable assigning of the start of chemistry. And really with Boyle, then we want to take one step back into, well, where did he start from? And that would be from Van Helmont. So when we're looking at Boyle, first of all, he is, I think, the 15th of 15 children. His parents are insanely wealthy, so he has access to lab equipment. He has people that hired servants that can help him work experiments. He has access to education. He has access to lab space, all the things that might not be available to the majority of people in the 1600s. Van Helmont came before him. So Boyle is reading Van Helmont's work and going, wow, this is really fascinating. I'm intrigued by this. And on this particular page, you see an introduction to a book that starts with an experiment by Van Helmont where he took a tree and planted it like a little sapling into a pile of dirt that he had carefully dried and measured the weight of. And then for 5 years, he grew a tree, and this tree grows to be huge with it only adding water. And at the end, he takes the tree out and he dries out the dirt once again and finds that the mass of the dirt has remained constant throughout those 5 years. And so Van Helmont then develops this idea that a tree must be made entirely out of water because there was nothing else that was added to it. Now, of course, Van Helmont doesn't know at that point about gases in the same way that we do. And so there's actually CO2 being added as well. But Van Helmont starts to do experiments with gases, and that's where Boyle kind of initially steps into the foray. So after that, a theory emerges called phlogiston. And phlogiston theory is very challenging because it's used to explain anything, but it's not very precise at making predictions. It's more just something that's inconsistently applied to explain different phenomena. So I want to actually go through and look at what they would have done with phlogiston theory back in the day. So the first thing that would get explained would be combustion and burning things. So when we take stuff that's flammable and that stuff has phlogiston, which is this little Phi symbol here, when we ignite it, we turn it into ash, and then that phlogiston goes off into the air. And the reason why we say the phlogiston goes off into the air is because they did know at this point that if you were to burn something in a closed container, that the phlogiston would not be able to continue the burning. So that must mean that the air at some point becomes saturated with phlogiston. So of course, in today's models, we would explain that a little differently. We would say that we're running out of oxygen. In the past, in phlogiston theory, they were explaining that the air was saturating with that. Interestingly, they also were aware that metals can burn. And so in this case, we have the metal and phlogiston burning to end up producing calx, and then the phlogiston gets released to the air. But this is interesting because what we know, of course, is that calx, let's say this is magnesium. If we're burning magnesium, we end up with magnesium oxide. The mass of that has gone up. And so in the first example, this could somewhat align and make sense with certain observations because the ash has a lower mass than the original stuff, and so we've lost this mass of this phlogiston. Whereas here, when the metal and phlogiston burns, we end up with a calx that's more mass. And so this was challenging to explain, And there were eventually some unusual theories as we start to blend in what exactly phlogiston is. Initially, we would have thought of it as the CO2 and steam leaving the system, even though we didn't know the specific chemical nature of that back then. But as we add into the metal piece, we start to run into other issues. For instance, you could take a metal and add acid to it, and that would displace hydrogen gas. So there was a theory, well, maybe there's this other type of phlogiston, or maybe phlogiston sometimes has smaller mass, or maybe something else is going on. And so some of the people would explain this by saying that the phlogiston was so light and low in density that the buoyancy effect made the mass appear to go up, which of course doesn't hold very well, but you get the idea of how they're going to inconsistently apply this phlogiston theory to explain anything, which then renders the model to be not an effective one. Another example of this would be here's zinc. So if we take zinc and we were to ignite it, we would release the phlogiston, we would produce this calx, which I would call zinc oxide. Okay. And if we take that calx and add sulfuric acid, we would end up with zinc sulfate. If we take zinc, which still has the phlogiston, and add sulfuric acid, we end up with the exact same chemical, but now we release this phlogiston, which is hydrogen gas. So in the phlogiston model, this makes sense. When Antoine Lavoisier comes around and says, hey, you know, this isn't particularly logical, the issue he runs into is people would say, well, what about this? How would you explain calx in a chemical and zinc with the phlogiston with that same chemical ending up with the exact same product unless there's this phlogiston? And of course, at this point, we're not detailed enough in our chemical composition to understand what's going on there. What's going on there is that the oxide component of this is reacting with the acid to produce water, but there's already water in the solution. So when they're doing this, they're drawing off that water and vaporizing it, and they're still just ending up with the exact two things, but really there was an additional product here. And so things like that were really challenging at the time to undermine. Now Joseph Priestley is our first to work on coming up with how to undermine that particular set of information. And Priestley, of course, inspires Lavoisier with his experimental evidence. Now, Priestley was big into phlogiston theory, and he died still believing in phlogiston theory. But he would do the same experiments as Lavoisier. Lavoisier would repeat them, but he would reach different conclusions. And so if you read Lavoisier's books, he'll actually diagram what some of these things look like. And what you'll notice is that they're very large. There's an intensive amount of mercury used in all of them. These experiments would take 4 or 5 people sometimes to manage the heavy weights of the mercury. But over the course of this, they end up with some highly precise data and information that they're able to construct for Lavoisier to undermine this phlogiston theory and say, no, there's a better model that we can use for this, where we use this stuff called oxygen, and the oxygen plus the stuff that's burning produces 2 other chemicals, and I can show how much of each there are. And so we can do combustion analysis and things like that to come up with a better thing. But I would say that Lavoisier, he was killed. He was a tax collector, so he's very wealthy and very hated, especially near the end by several of the French Revolution. But when Lavoisier is doing his work, he's also running into struggles where he can't explain certain things. So like that zinc and sulfuric acid thing, but also there was another problem, which was, why do some things burn and other things don't? If I start just trying to light various things on fire, some of them will burn, some of them don't. So if it's not a phlogiston thing, what's going on there? Now in today's world, we would go a step further and say, well, that's based on the bonding structure of what will and will change into a more stable substance upon the addition of oxygen or some other oxidizing agent. So Lavoisier didn't know that. And so he ended up producing another theory called caloric theory that was an attempt to add some kind of explanation. And so this caloric theory was that there's a given amount of caloric, which is this, fluid within substances, and I believe it was massless in his case. And this explained the energetics or thermodynamics of what chemical reactions would and wouldn't happen. Now, this was later disproved by friction. So we could produce an unlimited amount of energy through friction by using an external source. So if the source of that energy was caloric, it would eventually run out. And that was found not to be the case. So these are really interesting kind of ideas of the progression of things. But after Lavoisier is working for a while, he does do one more really important thing, and that is he sets the table for naming chemicals. So prior to this, especially when we're looking at alchemy, there's inconsistent nomenclature being used, and in different parts of the world in different languages. So communication between scientists and chemists is very challenging to do. And so in 1787, Lavoisier and three other scientists write an established method of naming chemicals. And so this book gets published. And what this does is it comes up with a compositional based nomenclature system. And so from there, we're doing naming systems that explain what the composition of things are. So at this time, for example, they wouldn't know what the formula for sulfuric acid was. Okay. But they did know that sulfuric acid had more oxygen content than sulfurous based on the ability to produce the two, using more oxygen when we burn sulfur to make sulfuric acid than sulfurous. And so they come up with a naming system that reflects that. And that's a really big step forward to being able to go on and do more than that. But it leaves us with a problem, and that is we don't know what the different chemical formulas are. And we also don't know for the elements at this time what their relative masses are, which is kind of one equation with two unknowns. And so we're stuck. Basically, in order to figure out, how much more massive a carbon is than a hydrogen, or an iron than an oxygen, we would have to know the formulas of some of the compounds that they form. But in order to find the formulas of the compounds, we would have to know how much the relative masses are. So for example, in an experiment, I could take 8 grams of oxygen and 1 gram of hydrogen, and I end up with 9 grams of compounded water. But I don't know whether that's forming, one equivalent of HO, where the oxygen is 8 times the mass of hydrogen, or something else. Maybe that's something where 16 grams of oxygen, or the oxygen is 16 times as massive as the hydrogen, but I'm doing 2 hydrogens for every oxygen, or something else, right? So we get kind of stuck at the end of Lavoisier's time, and it wasn't until John Dalton comes through and says, well, let's just make it up. Let's just pretend we know what the answer is. So we don't know that this is right, but John Dalton says, well, let's assume one, and then we can figure out the other. And this is brilliant, even though the execution isn't perfect, because what it allows us to do is start with an initial set of relative masses. And so you can see these are some of Dalton's relative weights here. From that, we can then test that. So we can look and say, okay, well, does this measure up? Does this measure up consistently in different compounds? And also, is there anything else we can do to check this? So you can see Dalton's work here, and we can compare that to today. And there's a couple things that should jump out. One is that Dalton is off by a factor of 2 and then some. So he's getting values that are 1, 5, 6, 7, 9, when they should be 14, 12, 16. Okay. So what Dalton is doing is he's assuming that the formula of water is HO. And because it's H2O, he's counting 2 hydrogens as 1. So basically this hydrogen is 1 should be 2, which means all of these values in this table should be doubled. Okay. But they don't know that at the time. Okay. So that creates a little bit of an issue. And then also just it's hard to make these measurements at the start of the 1800s in a precise manner. Now, Berzelius follows up with Dalton's work, and Berzelius is going to be who we talk about next. Now, I want to point out before we get to Berzelius that from Dalton in our chemistry classes, we usually stop there. Maybe we talk a little bit about Proust and multiple proportions or definite proportions. But from this point on in history, we kind of skip over all the way to the 1900s in quantum, or Rutherford and then quantum, right? So what is missing in that segment is the buildup and solutions that are gradual and very confusing to what happened next after Dalton. So let's go back to Berzelius and look at this. So Berzelius, this is 1826, and you can see his atomic weights versus modern atomic weights. And so when we look across, we see that there's a very good agreement. You also notice that he's different than Dalton in that he's not assuming water is HO. So his relative masses are in line with the modern atomic weights. And this was something that was a big issue throughout the 1800s, was that different people aligned with different scientists. So Dalton and Berzelius have 2 different sets of relative masses. Some people wanted to use Dalton's. Other people wanted to use Berzelius. Other people might have had other relative masses that they used, based on what their starting assumptions were. So these could all stem from the same experimental evidence, but based on the assumptions made about the compounds, we would end up with different things. Now, one of the reasons why Berzelius is able to come up with a better set is because two other scientists, Petit and Dulong, find a correlation between atomic weight and specific heat capacity. So interestingly, if you think about specific heat capacity, for a given type of substance, the more particles you have is going to implicate the specific heat capacity per gram. And so specific heat capacity declines with increasing atomic weight. And it does so mostly proportionally. And so this was a great check for Berzelius to come along and say, oh, you know what? Dalton was assuming something, but his assumption must have been wrong because this aligns with specific heat capacity data. And so we end up with a improvement upon that, but we don't end up with consensus amongst different chemists. And that makes things very challenging as we're going to move into organic chemistry. And in organic chemistry, we're looking at carbon, hydrogen, and oxygen-based compounds, but understand that the formulas of these are very complex. We're not looking at H2O now, we're looking at C6H12O6, or we're looking at C4H10, or we're looking at CH4. And so the variety of things that are very similar makes it very challenging to then deconstruct what the formulas would be. As we're doing this, let's keep in mind a few things. One, there's going to be discrepancies over relative masses. There's also going to be problems with diatomics. So at this time, there was not a consensus on whether nitrogen, oxygen, the halogens formed diatomics, because Dalton, he assumed that it would be impossible for two hydrogens to stick together because he's using the dualism model from Berzelius, which said that hydrogen is a positively charged thing. And so to have two positively charged things stick doesn't make any sense. Other people are using gas experimental data from people like Avogadro that are saying, no, there's evidence here when we look at the combination of these gases that there must be more particles within a molecule of hydrogen or of oxygen or of nitrogen, and therefore there must be diatomics. At this point, there's no bonding theory other than dualism, and maybe getting into a couple other organic chemistry bonding models. There's no periodic table, so we have Berzelius list of elements, but there's no periodicity. There's no mole for another 100 years. So it wasn't until right before the 1900s that the mole comes about, and we don't know anything about structure. Okay, so these are all the things that we don't have at our disposal to do analysis of. What we can do is we can figure out masses and relative mass assumptions, which brings us to Liebig. So Liebig studies under Gay-Lussac, as well as some other people. And in the 1820s, he gets into a fight with Wöhler, who studied under Berzelius. And the discrepancy is that Liebig synthesized silver fulminate. And you can remember Liebig does the fulminate because Liebig, as a small child, was fascinated with explosions. And so obviously fulminate's an explosive. And he finds that the formula for it is AgCNO. Okay. And Wöhler published that Ag, we could call it AgOCN now, but at the time it was been AgCNO was the formula for silver cyanate. And so they find each other's published works, and they Liebig calls them out, says, hey, you must be wrong. This is silver fulminate, can also be silver cyanate. Wöhler defends himself, he reaches out, and they decide to exchange information. So they exchange procedures and check each other's work. And after doing so, they find out that they both have the correct formula. So this is a really interesting discrepancy because we would interpret this today as an isomer, but basically there's this idea that there's two compounds that have the same chemical composition and yet they have different structure. Somehow, some way. We don't really have any insight into what that might be, but somehow these are different from each other. One's an explosive and I don't really know what silver cyanate's used for. So Wöhler and Liebig become best friends. They start to work together on stuff. They start to figure out stuff with organic chemistry. And Liebig, of course, blows up and becomes one of the premier chemists of the mid-1800s. So I happened upon a book while I was in Boston at a used bookstore. This is Liebig's Familiar Letters on Chemistry. It's quite old, from 1851. And I got to read that, and in this he talks about how they discovered what the formula for sugar was. And before we get to that, I also want to throw in, just for fun, that there is a full chapter on spontaneous human combustion and how Liebig is skeptical that that's a thing. He thinks there may be foul play afoot on the 40 or so cases of spontaneous human combustion. So it's always fun to read chemistry stuff from the past. Now, in this, What Liebig starts with is that 8 grams of oxygen, 6 grams of carbon, and 1 gram of hydrogen combine to make sugar. And from that, he wants to know, what is the formula of sugar? Okay. So if we kind of look in here, the first thing that happens is he comes up at the very top, actually, that there's this empirical formula of CHO. So he's using a relative masses for carbon and oxygen of 6 and 8, not 12 and 16. So he's working off of kind of the Dalton assumption there. So he's ending up with CHO as the empirical formula, which we would actually come up with CH2O for this particular thing. So he goes through and says, well, the empirical formula is CHO under his assumptions, and therefore the actual formula could be C6H6O6. It could be C9H9O9 or any other multiple of this. So the first thing it looks at is that when they take this sugar and combine it with lead oxide, that the 180 grams of the sugar combined with 1 equivalent of the lead oxide. Now they don't know if the 180 grams is 1 equivalent of sugar or if it's 2 or a half or something else. But this gives us some insight. So if they say that it is 1 equivalent, that would mean that 180 grams is equivalent to, one thing of sugar. And since C6 for carbon, 8 for oxygen, and 1 for hydrogen adds up to 15, if we compare 180 and 15, it's 12 times as much. So he then comes up with a potential formula of C12H12O12. But if it's 2 sugars, which we don't know, right? There's certain compounds where it's a 2-to-1 ratio. If it's 2 sugars, then it would be C6H6O6. So then they go on and they look at, well, what happens if you do fermentation, where we take sugar and produce alcohol? And interestingly in here, you'll note that their formula for carbonic acid, which is how they would describe CO2, because back in Lavoisier's time, they described acids as the gas you would add to the water. So the acid was SO2 or SO3 or CO2. So, and you'll notice that it's carbon dioxide, it's in the correct formula, because without the hydrogen discrepancy, we do end up with the correct relative masses. 8 to 6 is the same ratio as 16 to 12. And so they do end up with the proper formula for CO2. But when they look at the production of the ethanol, which I believe is in here as C2H4O2, it's up here, C4H6O2, that this gives them some more insight on whether or not they're on the right track. Next, they look at the dehydration of it, and they find that the dehydration of the sugar removes 3 equivalents of water, which under Liebig is HO. So that means they're taking away 3 HOs. So if they assumed that the formula originally was C12H12O12, that leaves them with C12H9O9. But if they had assumed that it was C6H6O6, that would remove from 2 equivalents, 1.5 from each, which would leave them with C6H4.5O4.5. And so Liebig says that rules out C6H6O6 as a potential for this chemical formula. So this is the type of analysis that they would do in order to figure out what chemical formulas were in the mid-1800s. It was very nuanced, and it was a lot of combination of relative mass with stoichiometry, where they're doing chemical reactions and then comparing the starting and ending amounts of the different chemicals in order to try and rationalize what the thing might be. And often you see examples of this where they'll do multiple chemical reactions, and they've agreed upon, this is what we're going to say ethanol is, this is what we're going to say carbon dioxide is, and they can use that to figure stuff out. So the actual formula of sugar, Liebig's formula, he rejected this formula based on the fact that dehydration would make this end up with fractional amounts of hydrogen and oxygen. This is his formula of ethanol. So our actual is off by, he's using 6 instead of 12 for carbon and of course 8 instead of 16 for oxygen. Formula for carbonic acid was correct. And then the dehydrated sugar would have been this. So this is a really interesting kind of thing to walk through and try and figure out. Now, if you think of this from a student perspective, these ideas would be overwhelming to them because they do so little analysis of this type, where they're applying models of how we might, figure stuff out in terms of amounts of stuff. Now, this is Liebig's apparatus for carbon dioxide, and this is famous because relative to Lavoisier's big giant containers of mercury, this was a very small thing. It's got a name I don't know how to pronounce. and the actual container there has 3 bulbs with potash in it. So the CO2 would get passed through those. There's actually a correct direction to this. And that apparatus there, cliprat, is the symbol on the ACS symbol. Okay. And this was nice because a single scientist could do this analysis on their own. And so he could have some of his students doing this work, or he could do it himself. And it was much easier to contain and control, and therefore he's able to get more precise data than Lavoisier might have been able to. All right, so that brings us into the point where we come back to the thiocyanate versus fulminate discrepancy, and we start to say, well, some of these chemicals seem to have the same formulas, and yet they're different chemicals. And so Archibald Scott Cooper is the first chemist to construct images where there's implications about the structure and arrangement and the connectivity of what these things are. And you'll notice here that he's doing similar things to Liebig, where he's doing 2 carbons, which is really 1 carbon. So he has kind of a dicarbon thing. And this leads to some discrepancies where people look at this and they go, well, why are there always dicarbons? Shouldn't there be a single carbon at some point? Maybe carbon is really 12 grams relative to 1 gram of hydrogen and not 6 to 1. But Archibald Scott Cooper was one of the first to construct structural connectivity arrangements. And he was also the first to describe benzene as a closed ring. However, no one knew about it because his work never got published. And so he gave his work to be published, and his boss decided not to publish it. And when later Kekulé comes along and publishes his work, found independently, Archibald Scott Cooper gets really upset and kind of goes mad from that and ends up in kind of a tragic story as he kind of removes himself from chemistry. We know about him now because we've discovered his work. So before we move into Kekulé a little bit, this is a fun quote from Colby, where he's complaining about people like Cooper, not Cooper, but Kekulé, and how structural arrangements are lazy. That in order for students to really understand chemistry, they must go through and do the detailed Liebig level of analysis to have a full comprehensive understanding, which I find quite fun, that will maintain throughout the ages. All right, so these are some of the structural arrangements. Now the Kekulé models are these sausage models. So you can see here in the top right, these are some of the chemical formulas. Here's hydrochloric acid, or muriatic acid at the time. We have water, ammonia, oxygen, and then down here we have CH4, which is marsh gas, is what they called it back then. So Kekulé comes up with this valence model. And the valence model says carbon has 4 valences. So meaning carbon can bind to 4 other things. So this is not a model that's looking at valence bonding. It's not doing anything with electrons. It's just saying that carbon tends to form 4 connections. And this is actually something that you'll see me do with my class with Legos. And this is his sausage model down in the bottom left for CH3Cl. And these are the actual structures that he built from that. So in the top left, you see work from Crum-Brown. And these are some structural arrangements that are meant to be the same thing as the sausage models, just extended in different directions. So we're adding a little bit of potential shape to this, which was resisted heavily up and through the 1870s. And that's interesting because people just thought, well, how could you possibly ever know or figure out what the shape of these things might be? So what ends up happening on the way to that is that we discover optical activity, and then Louis Pasteur develops that with tartaric acid crystals showing enantiomers, basically, that some of the crystal structures are like one hand and the other ones are mirror images of those. And then Jacob van Hoff, he proposed tetrahedral carbon. Now he was not alone in doing this, so there's another scientist doing this as well, but he pursued it very aggressively to the point where he even constructed his own models and then took them around to professors to say, look, this is what a tetravalent carbon looks like, and here's how I know. And in order to do that, they had to kind of go, look, if these are at 90-degree angles, then CH3Cl should have 2 different CH2Cl2, sorry, should have 2 different isomers. It should have one where the chlorines oppose each other and one where the chlorines are adjacent to each other. And so since they don't, there must be something symmetrical about these 4 valences of the carbon. And the only way for that to exist was with the tetrahedral carbon. So Van Hoff really puts the structural components and the 3D stereochemistry on the map at building off of the work of the other 2 here. Okay, so let's talk about teaching implications. Let's pause for history for a second here. So what do you do in your classroom with this? And I think that one of the important things for teaching is that students need to think hard about chemistry, right? If memory is the residue of thought, then that means we want to provide students with opportunities to think critically about these things. So some of the things that I recommend are having students examine evidence and develop models to explain historical dilemmas, like is this thing diatomic or not? What would the actual evidence for that look like? And then could they do that analysis? Have them utilize models that we don't always use anymore, like Dalton's models of the relative masses, or Liebig's, configuration of figuring stuff out. Have them use calculate sausage models. They're fantastic. They'll set them up to really understand Lewis structures well. In order to do this, you might have to adjust your sequence. So you can't be doing electron configurations early in the year and then expect students not to use that to then address some of the discrepancies you're presenting to them from 1820, 24. They're going to use electron configurations. You might want to hold that off until later. But without doing this segment of history, we're missing out on some opportunities. And I think also one of the things that I've really enjoyed is that students should see how the smartest scientists struggle. These are the most brilliant people in the world, or some of the most brilliant people in the world, and they're struggling immensely to figure this stuff out. They're wrong constantly. And really not wrong, but their assumptions are no longer what we assume anymore. We've gotten to a more advanced model. And I think that students currently have issues with seeing smart as knowing everything right away all the time. And that's not really what it's about. It's about being able to do the deep thinking and critical analysis that we want them to do. We want them to do what Liebig did. Even though he ended up with C12H12O12, we want that analysis of like, how can I figure this out? So here's some student work. On the top left here, you can see students who are constructing two hypotheses for copper and oxygen. In the first one, the copper and oxygen are the relative mass is 1. And in the second example, the relative mass is 4 to 1. So copper is 4 times as massive. And so we end up with Cu4O, Cu8O in hypothesis 1. And then for hypothesis 2, we have two compounds, CuO and Cu2O. And so you as a teacher will probably recognize that and go, well, obviously the hypothesis 2 is correct. But this allows them to look at what relative mass is and how we can use this to hypothesize what formulas might be. This is very similar to Dalton's work. You can see the same thing on the top right with carbon and oxygen, where we're looking at either a C3O4 or C3O8, or we're looking at CO and CO2. Then later in the bottom left, the students are applying that where they're figuring out the formula of zinc chloride, which of course we're then jumping in and saying, well, could it be, Zn2Cl4 or some other combination like that? Getting at the idea of empirical formulas. On the top right here, you can see the students doing analysis of gases combining to make different compounds. And on the bottom right, this is the LEGO activity. So this is the idea of valence from Kekule, where we're looking at two different structural arrangements of C2H6O. And in one we have ethanol, and the other we have dimethyl ether. And so that is a particularly really cool exercise where the students get to figure out, how could the connectivity be different for the same composition? And that allows the students to really identify with composition as a primary component of what identifies a compound. And that's not always clear when we just start with abstract definitions early in the year when students don't have a ton of chemical knowledge to draw from. So I've compiled some resources here. Gases and how they combine is a set of video evidence from the 1950s. I hope that someone remakes it. I hope to one day, but in the meantime, it's very exciting, but students won't know because George Pimentel is the person who does the things, and he's a little bit monotone. American Modeling Teachers Association is a great resource to be able to find some of the things if you like some of the work that I just showed with what my students did. And then also, if you don't have Legos, you can do them virtually. And then also the lectures on this series, this is a Yale chemistry professor in physical organic chemistry. And the historical components from 19 to 24 were fantastic. I loved watching these. They were super helpful to kind of help me tie things together that I had read about. Another thing that I want to throw out there is that there is a history of teaching within this. So 1872, Edward Frankland put together a book, How to Teach Chemistry. And if you read it, it is amazing. It is incredibly dangerous. It looks so fun. I would absolutely teach it for half the salary that I get now. But it is treacherous. It is nonstop evidence-based. And I think that's really critical. In the 1870s, you had to convince people of what you thought. And in the 2000s, we don't need to do that anymore. A lot of people accept claims based on authority from a textbook or from a teacher or from a video. Whereas back then, this whole book is show that the composition of NO includes nitrogen by doing this procedure. Everything is macroscopic lab evidence. There's no kind of unfounded claim within that book. And there's another education book that I haven't read yet, but I'm going to talk about later. I'm going to skip over Cannizzaro to maintain our time here a little bit, but I left the notes in there for what he did as well as some of the others as we're building for periodicity. And same thing with bonding theories. I'm going to leave those out, although they're very cool. This is a compilation of some of the lesser known chemists. Some of them are well known, and some of these are so overly reductive it's insane. But I hope that you get a chance to look into a few. Later, I'll leave those up. And then random fun stories from history are so critical when you're teaching chemistry. You want to be able to do transitions frequently and to be able to pull in, really valuable lessons like the Wöhler versus Liebig, but also just interesting stories like James Joule, or even something that's about equilibrium that's a complex idea thing or complex content area. Lord Rayleigh in particular is one of my favorites, looking at the two samples of nitrogen, one from the removal of oxygen from air, and the other one where he generated nitrogen from ammonia, and how that slight difference statistically showed that there's something else present in air, and they discovered argon eventually by doing the emission spectra from it. All right, the last thing I definitely do want to do though is I want to talk about books. So I am doing this because I have been enamored with reading books about this, and I wanted to kind of give you some guidance on what you might find. So the first book on here is by Partington. He's a student of Walter Nernst, and he was the first person to really put together what is the history of chemistry. That is the short history of chemistry. I have not read the full version of it, but this is an amazing book. It is just absolutely loaded with information. I would love to read the long one if I can track that down someday. The other book that is at the bottom left here is The Development of Modern Chemistry by Aaron Ide. Aaron Ide was a student at University of Wisconsin, and he actually, I think, just passed away about 22 years ago, so I think he made it to see Google. But that book, every story that I've ever read that I've loved, like Deborah Bloom, Sam Keen, all of those fun chemistry authors, Eric Sherry, these are all in here. All of the stories are in here. In fact, there's more to tell, I think, that go beyond some of the ones that have already happened. Of course, there's a wide variety of books here that are also very good. I enjoy reading some of the older chemists, but I would say Robert Boyle was awful. I hated his writing so much. Lavoisier was much more fun to read. And the only issue with his was that they have the Old English S, which looks like an F. Alan Rock, Professor Rock, is at Case Western, I believe. And his book here, he was nice enough to email me with a little bit about chemical history. I believe he teaches a course on it. And this is one of his books, and it was about how being able to visualize chemistry and imagine opens up the door for creativity and experimentation and the evolution of conclusions and models. That was a very, very good book. I really liked this one. Antimony Gold and Jupiter's Wolf is on nomenclature. It's on, the sources and etymology, name origins. And as a chemistry teacher, you'd be surprised at how much value that can add just by adding a small detail that a student will recognize in their brain as, oh, I know the correlation between those, and they'll feel more confident. World on Fire is a look at Joseph Priestley and Antoine Lavoisier. Poison Squad's a great story by Deborah Bloom. This book down here, Great Physicist by Cropper. This one has a great thermodynamics section, and probably the best of the ones that I've seen. So if you want to learn about the evolution of entropy, enthalpy, those big ideas in temperature and heat, this was fantastic. I use this all the time in my teaching. In addition to those, these are some other ones. I think I just saw a disappearing spoon on both. Whoops. This Rutherford book I found at a bookstore, and this was really fun because it was one of those Kids These Days books where it was lecturing kids on, back in Rutherford's time, he didn't have it easy like you young whippersnappers. He didn't have stores that he could go to, or roads, or cars. Eric Sherry, of course, on the periodic table is bar none, hands down the best. Periodic table, Story of its Significance is the best book, but Tale of Seven Elements is just a great story about the when Moseley determines the atomic charge can be determined through interactions with X-rays and basically provides an answer key. Prior to Moseley, there have been heavy disputes about multiple element discoveries. Then all of a sudden, those all get settled in 1 year, and they reveal 7 elements missing between hydrogen and uranium. And so the search is on. Chemistry of powder and explosives was interesting, but not for the whole book, I guess I would say. It was very redundant. It was just a lot of really dangerous, cool stuff from history and that you could do. But for a high school teacher, most of those were far out of my reach. A lot of picric acid in there. What else? The William Brock chemistry history book was similar to the Partington and the Ide books, but it was more recent and included some new things in it. So I enjoyed that very thoroughly. Some of these I've read since then. The Frankland book and the Chemical History Tour. This one's got a lot of really fascinating pictures and images from sources. But the one I'm really looking forward to read is Jane Marcet's Conversations on Chemistry. And she was a chemistry teacher back, I think, before Frankland even. And I think potentially it was illegal for her to teach back when she did. But oh yeah, it was before, because she was the teacher that inspired Michael Faraday, if I'm not remembering incorrectly. And he read her book, and that's what got him to go into chemistry and to seek out the Royal Society and to work under Humphrey Davy. So these are some of the books that I'm hoping to read coming up. And then, of course, these are the two big ones. If you start with these, what I'll tell you is that as you read them, you'll be so unfamiliar with so many of the characters. Like so many of the scientists, you'll recognize their name and you won't really know what they do. And the interactions between them take time in multiple books to really kind of get a sense of what happened, especially because you're dealing with outdated models of the chemistry itself. And then, of course, this was absolutely fantastic thermosection. So that's kind of the journey that we've taken. I appreciate, anyone who attended tonight. And if you have questions, feel free to reach out to me on Twitter or talk to me somewhere. I've really enjoyed learning about this. If you have stuff to add, I have not been formally trained on this. I have loved reading about this. If you have other book recommendations or anything like that, just go ahead and let me know. But otherwise, that's it. Thanks so much.